you ever go to try and put an assembly together and then realize the bolts don't fit right? Well, in this episode, we're going to be talking about how to properly select the right size fastener, how to tolerance it, and put it on your drawing so that you can actually get your assemblies to work the first time and make sure that there's a consistent way that you're designing your components. Welcome back to Engineering Aerospace with me, Eric Kane. Today we're going to be talking about bolt holes, and it sounds kind of simple, but holes are everywhere when it comes to engineering, and understanding the appropriate dimensions to be using, the proper callouts, tolerances, etc. for the applications that you're using them in is an important aspect of design that you need to consider. So today I wanted to kind of talk through some of the basics of how you determine what are the appropriate sizes for fasteners, how do you tolerance holes for particular applications, and what does a drawing callout look like. Now, of course, there's a lot of applications, reasons you might create a hole in structure, and the obvious ones, of course, are things like attaching fasteners, bolts, rivets, that sort of thing. You may come across things like high locks or eddy bolts, which are effectively somewhere in between a rivet and a bolt. They're kind of a semi-permanent bolt. And those require certain types of holes to be applied for each of these cases. And depending on when and where and what assembly and how critical it is and what kind of tolerances you need on that can define what size and type of hole you're going to use to install a fastener. So there are, of course, other applications. You may have things like alignment pins where you have a very tight tolerance where you need to have like an assembly that comes together. Perhaps it's removable, but you need that every time to align to a high precision. This may happen a lot with precision sensors, navigation equipment, that sort of thing, where alignment is very key to the function of that hardware, and having a repeatable alignment feature is useful. And so a lot of times those tolerances are super tight, and so understanding how to appropriately tolerance a hole such that you can get them together, but they're not so tight that you have to force the installation. So let's start by kind of talking through the different sizes that you're going to come across in fasteners. We'll start with the simple cases of like a nut and bolt kind of situation. And what I've got here is an example of just a general bolt specification. This is the old AN Army Navy spec for standard fasteners, and so they had a standard for AN3 through AN20 in this case. Number 3 is just the size for what amounts to a number 10 bolt in general applications. So you can see a 1032 fastener call out here. And I can even zoom in a little bit for you to see that better. But this is just a very standard aerospace bolt. It's kind of like the bare bones kind of fastener. If you're using one of these and you want to pull up the spec, you can pull this old Army Navy spec from the federal government's the Quick Assist site. If you search Assist Quick Search on any browser, it should bring you to a website that allows you to search government specifications from the U.S. government, and you can find this document in there. The other thing, of course, though, is that most of those government specs are now transferred to other commercial organizations or industry organizations, and so this fastener spec is technically superseded by a more current NAS, National Aerospace Standard spec out there, but most of the, for educational purposes, this is plenty good enough. If you are working, in a professional environment, you should probably pull the latest specification to be sure you have the correct data. But in any case, this is just a standard bolt, so I'm not too concerned here. But the important aspects that I want to highlight here is that every fastener is going to have some tolerance to its diameter. So in this case, the drawing here shows that letter A is the dimension for the bolt diameter. So if I go down to the specification table and look at the specifications for letter A here, I can see it listed it as a minimum and maximum dimension. And in this example, we'll be talking about the AN3 bolt. And so a 1032 is sometimes listed as a 0.190. That's a 190 diameter fastener, and that's the dimension in inches, so 190 thousandths of an inch. What you'll see here is that the actual direct measurement of the bolt is somewhere between 189 thousandths and 186. And so, there's always a manufacturing tolerance. It's never perfect. And so this is a pretty standard loose tolerance, if you will, for a bolt. If you're looking at something like an alignment pin, it may have tolerances down to the 10 thousandths of an inch because it's very precisely ground. And a typical fastener like this, a couple thousandths variability in the diameter is pretty common. So you need to be able to make sure that when you're sizing a hole for this bolt to go into, that you've accounted for the potential variation in the bolt diameter. And if you want the bolt to go in freely, you don't want it to be a hole smaller than this 189 or even at that 189, because now the friction and the interference is going to be too much. So that kind of leads me to, let's talk about the basically the different types of fit that you're going to come across when it comes to fasteners. So there's really kind of three major classes of fastener fit. And the first, of course, is let me see if I can turn off the assistance here because it's trying to draw straight lines. The first is going to be a clearance hole. And so this is a situation where you may have a bolt, right? And the hole that it's going into has clearance. And so there's space, right, that you can see between where the bolt goes in and where the edge of the hole is. And so obviously the hole is bigger than the fastener diameter. Another one is an interference. And I probably can't spell that right, but you get the idea. Interference fit. So in this case, if you have a bolt, more often you might have something like a pin. The actual hole diameter is narrower than the diameter of the bolt. And so now you have an interference region. And so, you might think that doesn't work. Well, with enough force, any material is going to deform and stretch. Metals are particularly good at this. So it's not that uncommon to see press fit installations for things like pins and bearings, and occasionally even bolts, where you want to have a true full contact in there. There is zero room of play in the bolt, such that the hole is completely filled. What'll happen is you'll actually work harden the material in these regions. And that can actually locally strengthen the material a little bit, but or at least make it more resistant to fatigue cracks and that sort of thing. So there are applications where an interference fit may be necessary. But if you want this joint to come apart, probably a bad idea. So that's something you have to consider. Now the third is what would be called a transition fit. So all these fits, this is just going to be like a crossover, right, between these. So you dimensionally, in some cases, might have an interference. In some cases, you might have a little bit of clearance. And so that the tolerance overlap in the bolt diameter in some way kind of overlaps the hole tolerance. And so, there's potentially some uncertainty there. Usually it's fairly narrow, and so that you have, a pretty good interference in the sense that you're going to take some pressure to put the fastener in, but it's not so tight you're permanently deforming materials and causing, the joint to become a more permanent installation. So it's kind of somewhere in between. It's not something you see a lot, but it might be something where you want a really tight hole fit, and you can accept a small amount of deflection in the material if it comes to it, but you don't want to leave a lot of play in the joint. So those are kind of some of the basic types of classifications you're going to see. every company is probably going to have its own standard as to what constitutes a clearance, a transition fit, or an interference fit. If you're not really sure, there's also an NAS. Let me check. I have it somewhere over here. NAS standard that actually defines this. It's a fairly complicated standard, so it's not something I necessarily want to go over today. NAS 618, that has a lot of details about different diameter tolerances on bolts and classifications of hole sizes and what are typically used for some of those types of crossovers. But we'll talk a little bit more about our example here. But if you need to and your company doesn't have a standard, that's something you could pull up and see if the company has access to this spec. If not, you can probably ask to get it purchased. It's not terribly expensive, but most companies will probably have standards in their mechanical engineering guide. And if your company doesn't, then maybe there's an opportunity for you to help create an engineering mechanical design guide to help engineers be consistent and use a standard. So let me clear this real quick, and we're going to go talk briefly about what kinds of typical hole sizes that we're going to use. So usually, like I said, most companies will probably have their own standards, but in this case, we're going to talk to the specifications for an NAS or an AN fastener. So again, we're going to use an AN3 bolt. And we looked at that earlier, and the diameter tolerance is between 186 to 189. So if I'm going to do some sort of interference fit, then obviously if I'm at around 186, that hole's going to be fairly small. It's 3,000 smaller than the possible top of the bolt size. So you may want to look and see whether or not that's something, can you afford that much interference? An interference fit, you probably don't want that much variability. There are better bolts for that where they have a tighter diametric tolerance, and so that you can be more assured of what that interference is. And right here we're looking at 0.003 of an inch variability, which is a fair amount when you're talking about actually interfering with something. Even if you're like line to line or even 1,000th, sometimes there can be enough friction in the alignment of the system that getting a bolt to go in may require a little bit of extra force. So adding 0.003 is a fair amount. Whereas if your bolt is, for example, only like 1,000th of variability, your hole can have perhaps 1 or 2 thousandths, and then the range of possible interferences is much smaller. Versus if I, for example, set the hole here to something like 185, it could just be 1,000th of interference, but it could also be up to 4. So that's a lot of variability that you may not want to have in your interference fit. So again, interference fits aren't always that common. Talk to a machinist, talk to some of your manufacturing engineers if you're not sure what kind of size interference you need for a particular application. But I do want to talk a little bit more about typical clearance installations, because those are far more common for us to use with bolts. So let's talk about what a typical hole size is for a fastener like this. Well, if you go look at the drill sizes charts, and you can just look them up online, there's, it's a universal standard. We typically use in aerospace, of course, English units, at least in the aviation world. You get into space, there's more metric, but there's still a lot of the manufacturing is done in the U.S. using the standard fastener sizes. So those will be things like, fractional, numbered, and letter bits, right? So these are the different sizes you'll see in a drill assortment. If you were to go to the hardware store and buy them, they're all the same sizes. But if you look at the decimal equivalent to all of these, you're going to see exactly what these units are. And so let's just take for example a couple sizes. So if I look at a number 12 drill bit, that actually has a dimension of 0.189. And of course all these will be in inches. But you can see that's basically line to line with the largest diameter of the bolt. This would probably classify as a transition fit if you were to drill a hole to this size. If I start going bigger, which of course the numbers get smaller when I go bigger, but you're going to have 191. Number 10 is, well, depending on how precise you get, 1935. Number 9, 196. I'm going to skip a few here. We're going to go up to 7. And skip a few more, and we'll go up to number 2. So you'll see here in a second why I'm picking these, but so these are kind of common drill sizes that you see in a range that might be useful for a fastener like this. So why might you want to choose any particular one over another? Well, like we said, this is probably kind of like a transition fit. This is a little bit, perhaps, we've got maybe 0.002 of clearance if you're at the big end, maybe 3 or 4 if you're on the smaller end of the bolt diameter. So that's a pretty snug fit, but it is a clearance. So this is this is starting to get into the clearance fit. It's probably worth stopping for a second to talk about tolerances, right, for fasteners, not just fasteners, but holes, sorry. When you're drilling a hole, there actually are tolerances that you have to count for the drill bit itself and the manufacturing process. So if you're unfamiliar with what those standards are, there is again another national standard out there which is pretty much out of date, but that it still holds. People use it still for reference, so I'll show you that here. This is the AND 10387, another old government specification. Technically, again, it's not active, but if you're not sure of what the tolerances are that you should be using for hole sizes, this gives you a good reference to start from. There may be some other NES specs out there. This is the one I'm familiar with, but you can see here, for example, if you have something in the just under 1/4 inch range, that you're talking at about plus 0.005 minus 1,000. So when you drill a hole with one of these drill bits, it's possible it could be maybe 1,000th under the dimension listed, or it could be up to 0.005 larger. And so again, you need to account for this in your manufacturing techniques and how you're speccing drawings out. And so if you need a tighter hole than that, now you're starting to talk about different manufacturing techniques. You don't want to drill it. Perhaps you're going to ream it. If it's a much larger hole, then perhaps it's turned with a lathe or something like that, and you could get grinding involved. But the general manufacturing process in this case is using a drill bit. So if you're using a drill bit with a machine or hand drilling, you can't expect the hole to be any more precise than this. So if we go back to our dimensions here and we look at our typical tolerance, is going to be plus 0.005 or minus 1,000th. So again, right here, as I'm looking at this 191, I could be down to 190, which still technically has clearance to that 189. So that's a pretty decent, application. And so if you need a clearance, but this is more of like a tight fit clearance, right? So this is if you need a very close fitting hole, but you don't want it to actually interfere. Now, what this of course means is there's basically just enough room to get the bolt in. Now, if you only have one hole, that may be perfectly acceptable. So perhaps you're using a P-clamp or something, and it's not really located relative to anything else super precisely. Okay, great. You can actually tie that in very, very tightly. Although typically you don't need a super tight hole if you don't care exactly where the hole is. And so, you got to consider these things. Now, if you're having a super tight hole and it's got to be very precisely located to another one, if you machine these parts separately and that hole comes in just a little bit to the right, well, you've already eaten up all your tolerance, right? So you need to make sure you're accounting for the tolerances of the assembly and the manufacturing techniques as well. And so we're going to have to potentially add more flexibility into the design to accommodate, more manufacturing tolerances. So if we keep moving down the line here, we've got a few more thousandths here with the number 10 drill bit. So, that's getting up there. If we go to 196, this is actually a pretty common size I've seen for more just kind of a medium kind of clearance fit. And so that clearance can be useful if you want a reasonably tight fit, but not so tight that it makes it, very difficult to manufacture. And we'll come back to positional tolerances and that sort of thing, but this has some good utility in machined components. And so that's where you're going to see that used quite often. You go up to 201. This is a very common size that I've seen used on drawings as well. This is a little bit more of like a loose fit. And so this is where you've got a lot more play in the system, or you're more room for tolerances in the position of the holes. And so this is a pretty common size you'll see called for a number 10. Now, some applications you may even see it called out even higher. So you'll notice here that this is about 30 thousandths of an inch bigger than the bolt diameter. And so this is kind of like a very loose, depending on how you want to look at it. Now that's okay if your component doesn't take a lot of load. It's not expecting to see a lot of shear loads, cyclical loads. Maybe it's something like mounting an electronics box where it doesn't really care about being super precisely located. Maybe the hole tolerances again are a little bit looser. We'll talk about nut plates as well, right? A floating nut plate where the nut element kind of floats within about a 20 to 30 thousandths circle. And so having a hole big enough to accommodate the full float of that nut element can be useful. And so that's where this comes into play a lot. So let's kind of talk for a minute about tolerancing of everything in terms of the locations. So let me clean this up. So we kind of briefly talked about drill bit tolerances. And again, you can tighten some of those up if you use different manufacturing techniques. But, you want to keep this as simple as possible, right? Because, the more complicated, the more precise you get, the more expensive things get, the more advanced techniques you need. So if we're talking about drilling holes, there's a couple ways you can dimension these things, right? If I have a drawing, let's just say I have a part that looks like this. Maybe I've got a couple holes, and maybe they've got some sort of alignment. And I'm going to change the color here as we start drawing on this. So a lot of times, people are used to just using the straight linear dimensions. So you might see something listed like this, right? You're going to see a dimension here, dimension there. Let's just call this, y1, y2, and then maybe someone puts the dimensions here, right? x1, x2. So when you're doing this, you have some play that you can decide in terms of the tolerances. Now, normally, of course, chain dimensioning can be a tolerance stack up issue. So, if you wanted to locate these relative to, let's say this is datum A, right? If you wanted to locate these relative to that face, well, that's one thing versus locating them relative to each other. And so if you have a pattern like this, you may want to make sure your fasteners or your holes are located relative to each other, and not something where you might have, for example, a dimension set like this, right? Because it's not so much critical that the holes be positioned relative to this edge as much as they be positioned relative to each other. And those tolerances can be different, right? I can accept the whole pattern can move a little bit to one side or the other, but I want the holes distance to distance being consistent. And so, there's kind of this ordinate approach, and then there's this more like a chain approach where you do one after the other. And so depending on the application, you may want to consider one over the other, but the most useful one is going to be using a GD&T, where I actually don't even specify these. These are our basic dimensions, and then I would provide a call out for the fastener diameter, and then I would list a position tolerance. And so this position tolerance is going to be a little bit different than the linear dimensions. Typically it's some sort of diameter, and it might be, for example, 5/1000ths of an inch. So we'll talk here in a second about what that is. You'll usually have some additional datums that this is referencing, but if I went with the basic dimensioning technique, and let's just say I'm going to put x1 here, x2 up here. So if I was using this technique where I was measuring these linear dimensions, they're typically going to have some sort of plus or minus dimension to it. And if I say that's 5/1000ths of an inch, if I were to zoom into the very center of that hole and where that hole is located, that means the hole could be up to 5/1000ths in either direction, right? So that's 5, that's 5. It could be vertically, 5 up or 5 down. And these are in thousandths of an inch. So that's kind of the pattern you would get if you're following a traditional linear dimension. Now, if you use a GD&T approach, this defines your tolerance down here in terms of a diameter, and it basically says the whole width of that is 5. Right, but what you see is if you're comparing that plus or minus 5 versus a 5/1000ths diameter, it's a little bit tighter. Now I could also spec this as a position tolerance with a diameter of 10, right? So 10/1000ths of an inch might look something like this. Well, okay, that would have the same diameter as the outer dimension of that square. But now you'll notice I don't have all this excess region. Well, that's honestly okay, because you probably don't want the worst on worst anyway, or you can even spec it wider and go out. So this is just that typical hole dimensioning technique that you use with GD&T. And so we'll talk for a minute here about how that applies to the hole sizes we just talked about. But before we go too far with that, there's also, if you haven't studied GD&T, that's a whole other field of study that's probably worth learning if you're doing mechanical drawings. And so I think it's something that you should study more in depth. But another aspect to this is that you can define these position tolerances based on the relative size of the hole. So they have modifiers, for example, maximum material or least material condition. And so you can actually specify that, okay, this dimension applies at the maximum material condition. And of course, if you're talking about a hole, the maximum material condition is when the hole is as small as possible, which basically means if that tolerance applies under those conditions, well, if the hole's a little bit bigger and you go towards the larger size of the tolerance for the diameter, say 5/1000ths, well, now I can accept that much more uncertainty in the position of the hole. So if I go back to the diameter down here and I were to specify this, for example, as a 201 hole plus, let me make some room. And this is a plus 5 thousandths minus 1 thousandth, right? So that means that hole could be up to 206 in diameter. And the most material condition would actually be 200. So the max material condition, if that's where the tolerance for this position applies, well, let's say your hole were off by 6 thousandths instead of the 5 that's required by the drawing spec. Well, okay, you can open up 1 more thousandth in diameter, and technically you meet that. And that really has to do with how tight a bolt fits in there, right? Or some other pin. And so the idea being that you're trying to locate these holes such that I can, put two components together and run a fastener through them. Well, if the holes are positioned right, they all align. If they're out of alignment, they may not fit. But if I just make one of the holes a little bit bigger, suddenly everything works. And so that's what this is trying to communicate. Now, let's go real quick back to the dimensions we were talking about earlier for fasteners. So as an example, our bolt diameter is up to 189, right? Well, if we talked about earlier, we have examples of 191, 196, 201, and 221. So all these sizes have some corresponding tolerance allowance. We kind of talked about, like, here you're talking about potentially a minus 1 thousandth on that hole size. Well, that only gives you 1 thousandth of play. So really this is probably best if you're going to match drill this. Like if you're trying to fasten two components together, you want to make sure that those holes are drilled at the same time if they're at the same location. There may be exceptions to that, but that's such a tight fit. You probably want to start with a pilot hole that's smaller, get the parts kind of lined up so you can see where they're at, and then drill the whole larger hole up to size that's at the same diameter in the right location already. So you don't have to worry about positional tolerances factoring into this. Now the 196 here, well, you'll notice again, that's like a 5 thousandths. And so what you can do is you could potentially set this to a 5 thousandths tolerance in terms of position. Now, we've added another 5 here to this dimension. Well, maybe this is 10 thou. And then even further, you can position this out to 30 thou. So, and of course, the looser you provide the manufacturing tolerances, the easier it is to get components manufactured. They're cheaper. They're less likely to be, discrepant in inspection. If you're hand drilling and locating components, you probably don't want to go any tighter than 30 thousandths. A CNC machine might be able to hold 5 thousandths, but a person trying to locate and drill something by hand, it's going to have a much harder time. And so if you can specify a much looser hole, that gives a lot more flexibility to the installer. And so instead of needing $1 million CNC machine, now I can send a tech out there with a hand drill, right? So that's how these tolerances come into play in terms of manufacturing costs. Now, obviously there are advantages of machine time, can be cheaper to operate, but sometimes it's not practical, right? A lot of aircraft are still built by hand because it's very difficult to design machines to get up into some of these places. It changes a lot. So there's a lot of reasons why you don't see aircraft manufacturing quite to the same degree as automotive, where a lot of it's done robotically. But you do have to consider quite often hand fabricated components, in which case, locating those features is not as precise as it would be on a CNC machine. So let's briefly go back and talk about the dimension or tolerancing and drawings and how I call this out. Now I kind of showed it here at the bottom, but let's go over the components in detail. So when you're calling out a hole, let's say for this example, this hole over here, you're typically going to provide some sort of diameter call out, and that is clearly just the diameter. So in this case, let's say we made this a 201 hole, and this again is assuming the drawing's in inches. Now, the other aspect of this is how deep does that hole go? So a lot of times you will see a symbol like this that indicates the depth of the hole, and that should be typically the depth of the actual very tip of the drill bit. Sometimes, you may call this, for example, let's say it's 1 inch, 1.00. You may also see things that say through, and that basically means it goes all the way through the part. There's not even a depth to worry about, just go through. So, you can do either one of these. Measure it out if it's only going to a blind hole, or call a through if it's going all the way through. Then if you're going to want probably some tolerances on this if it's not drawn out somewhere as a standard on your drawing. So again, you may go back to your specs from the NAS standards or other company standards. So this might be a 0.05 minus 0.01. And then below that, if you're doing GD&T, this is where you're going to have your callouts for like your position, right? You'll have this position callout with some sort of diameter, maybe it's 10 thou, and then the datums that references in order. And so that's what a typical hole callout is like. Now in this case, there's 4 holes, and so we usually put a 4X up in front. Sometimes people have used typical, or they'll say PL for places, so it may say 4PL for 4 places. Kind of the general industry standard is to use a 4X to indicate there's 4 locations where that hole applies. Now if you have a lot of other holes that are nearby which might get confused, let's say there's another hole pattern here or something like this, and maybe these are different size. It can be handy sometimes to create some sort of label so it's clear, either using these dashed lines to clearly identify the pattern, right? Or you can use some sort of label that's on the drawing. And so I've seen examples where, I'm just going to use a different color here, where you might have all these holes labeled A and all these labeled B. And so when you're putting notes up here, you may say labeled A, right? And so that tells somebody that these holes are labeled A, so that applies to anywhere the little A call out is located. And that helps you differentiate. If you have a lot of holes that are kind of subtly different or potentially could get confused, that's a convenient way to do that. Okay. Well, I think that's all I wanted to talk about today. So that was a handful, and surprisingly enough, the holes can get very detailed very quickly. We didn't even talk about things like counterbores and countersinks, and we'll try to talk about that some other time. And there's a whole host of other topics we could probably go into when it comes to fastened and bolted joints. So let me know what you think. If there's other things you're interested in hearing about, we'll keep trying to put some content together and keep the information flowing. So until next time, appreciate it, and we'll talk to you then. Bye.